computer. Okay, cool. So welcome everyone. This is going to be Why Think, letting computers do math for us. So the idea is going to be to talk about various what are called decidability results in logic. And decidability is about taking sentences in some logical system and deciding whether those sentences are true or false. And so we're going to talk more about the specifics of what that means. But you can imagine this is a very powerful technique. And there's lots of results in the area, depending on if you're an optimist or a pessimist. And I guess depending on whether you want there to be results or if you want to have job security, your notion of optimism and pessimism might flip-flop. But there's lots of positive results and there's lots of negative results. So it's a very interesting thing to think about. I would like to change slides. Cool. Okay. So first, a brief review. If you were here for my talk last semester on model theory, we're going to be rehashing some very similar stuff. I'm going to go through it kind of quickly because we don't need as detailed an understanding of syntax and semantics in order to talk about decidability results. Just a passing familiarity will work. So in logic, we always work relative to some allowable symbols. So we have primitive symbols, which are related to whatever we're studying at the time. And we also have logical symbols, which are related to what particular logic we're using to study those objects. So as an example, when we're studying groups, we have primitive symbols for multiplication, for inversion, and for the unit elements. And if we're studying partial orders, we would have a primitive element or a primitive symbol representing the order. First order logic, which is the one we're most familiar with, has all of your common symbols. So you have and, you have not, you have quantifiers for all and exists, and you have other things you can get with these. So you can get like or, you can get implies, you can get by implication, etc. But there's other logics that people study. So for instance, there's infinitary logic, which for traditional reasons is typically called omega 1 omega. Which not only does it allow the stuff that regular first order logic allows, it also allows this infinitary conjunction as well as infinitary disjunction. So if I have countably many propositions, I can actually take the and of countably many things. Okay, which first order logic doesn't let us do. First order logic is entirely finitary. There's also this rather fancy one called monadic second order logic, which not only can I quantify over elements of my, for instance, group, I'm also allowed to quantify over subsets of my group, which gives lots of power. And the reason it's monadic is I'm only allowed to quantify over subsets. I can't quantify over, for instance, subsets of my group squared or things like that. Okay, and like I said, X is an element of the domain and capital X is a subset. Okay, so let's see what formulas are. So if we have a logic L, for instance, first order logic, and some primitive symbol sigma, we write L of sigma for the set of all formulas you can write using the logical symbols and the primitive symbols. And one of these formulas is called a sentence if it has no free variables. So let's see some examples. The standard thing, if you look at the first order logic in the symbol, in the whatever it's called, signature of groups, then you can write down this sentence here, which says for all x, x times 1 is x, and 1 times x is x. Easy peasy. That's something you can write down. If you allow infinitary conjunctions, you can write down this sentence in the language of successor and zero. So you can think about this as the natural numbers. And this says that every natural number is 0, or it's 1, or it's 2, or it's 3, or it's 4. I'm not going to list all of them because it would take a while. But you can see we're allowing this infinitary disjunction, which would not be allowed in first order logic. And for monadic second order, you can actually express the notion of a well ordering. So for all subsets, there exists an x in that subset, which is a lower bound, or which is a minimal element. Okay, so this allows us to express the notion of a well order. And then these are all sentences, but if you don't quantify everything, for instance, you can write this commutativity property. That is a formula with 2 free variables, x and y. And when I quantify over them, I remove the free variables. Okay, so questions so far. Hopefully this all makes some amount of sense. Okay, so a subset of L sigma is called a theory. So for instance, the theory of groups is given by all the sentences which you can prove from the group axioms. This is some set of sentences, and it's something which group theorists, for instance, are very interested in. And so why do we care? Well, let's say a slide on semantics, which is given a set X with functions or relations which interpret all of my symbols. So for instance, for group multiplication or for groups, I would need a function from X to itself or X squared to itself, which corresponds to multiplication, a function from X to itself corresponding to inversion. And I would also need a constant, an element of X representing the unit. So a thing which could be a group. Then we say that X models a theory whenever X thinks that every sentence in T is true. So a model of the theory of groups is just a group because we have actual functions representing all the symbols, and we think that the theory, which means we think that the axioms, are true. Okay. So let's now get to sort of the meat of the talk, which is the notion of a decidable theory. So a theory is called decidable exactly when there's a computer program that takes a sentence phi and tells me yes or no whenever phi is or is not in T. And such a program is called a decider for T. So there's some obvious questions that come up from this. The first is which theories are decidable? That's are there characterizations which tell us when a theory is decidable? And moreover, if we have a decider for one of these theories, how long does it take to run, right? Deciders become less and less useful as they take longer and longer to answer our questions. We'll focus on the first question because this is a math talk, not a computer science talk. But the short answer to the second question is a long time. It turns out solving logical problems is hard in a way that can be made precise. And if you're ever looking for hard problems, you should take an undecidable problem. For instance, deciding all of first order logic is undecidable. And you should just nudge it down a little bit until it becomes solvable. Oftentimes doing this, taking something impossible and making it possible, gives you something which is possible but very, very hard. And so, yeah, deciding various theories are sort of canonical examples of programs that take, for instance, doubly exponential time to run. In fact, I don't think I can think of another doubly exponential theory off the top of my head. Okay.
Question.
Yeah, totally.
What do you mean by computer program? Is there a short answer?
Sure. So I'm going to do the standard arm waving here. So if you really want, it means Turing machine or register machine, or I guess if you really hate yourself, something to do with Gödel's beta function. But we have a notion of computability, which can be made precise. And this notion of computability is very, very robust. So it turns out anything that could model computation, all of these things that we have checked, and we've checked many of them, turn out to be equivalent. So this tells us that we really are onto something, and it's not some, when we talk about a Turing machine as a model of computation, that's a reasonable thing to do because it turns out implementation details of Turing machines don't matter. So if you like, I mean, Turing machines, but pick your favorite model of computation. If you like, when I say a computer program, I mean a sequence of PowerPoint animations, which it turns out that's Turing complete. But yeah, that's roughly what I mean.
But you're not allowed to just say like, I want a computer that does this, and then you would have to like build it.
Yeah, exactly. So really, really interesting question is, when we show that a theory is decidable, how constructive is that procedure, right? So I know that the theory is decidable. Well, can you actually write me a computer program like in Python or Haskell or your favorite programming language? Can you actually write me a program that does it? And all of the examples that I can think of are constructive. So you can actually write a computer program that does it. I'm sure there are results where a theory is decidable, but we don't know how to write the program that decides it, but I don't know of any such results. Everything that I know, you could in theory turn the proof into a real computer program that does the thing. And people have. A lot of computer scientists are interested in that.
Okay.
Cool. Okay. So there's a useful lemma, which will provide some inspiration for the decidability results. And that is, given any computably enumerable set of axioms, where I'm going to explain that word in scare quotes momentarily, the set of theorems provable from those axioms is also computably enumerable. So a set is computably enumerable, or if you're reading an older textbook, recursively enumerable. So this is often abbreviated CE or RE, Your CE exactly when there's a computer program that will list out all of the axioms. So you can imagine most things that we're interested in do have computably enumerable axioms because there's like finitely many axioms and you can write them down and you can get a computer to write them down. This hypothesis prevents pathologies where if I just take every true sentence as an axiom, right, then that's silly. And so this prevents things like that. But it's a very mild assumption, I assure you. And so we want to know, how do I list all theorems? Well, I look at my first axiom and I look at all proofs of length 1 that use my first axiom. And then I look at all proofs of length 2 that use my first 2 axioms. And then I look at all proofs of length 3 that use my first 3 axioms. And I proceed in this way. And every theorem is the conclusion of some proof. And every proof only uses finitely many axioms and is only finitely many lines long. So every theorem shows up somewhere on this list. And so because I know I can list my axioms, I can get the first n many. And proofs are just basically combinations of axioms. That's easy to do with a computer. And so informally, I can list every theorem in this way. OK, so notice since I can list all the theorems, this does not mean I can list all of the non-theorems, right? Because so I have some infinitely long list of all of my theorems. And if I have something that I want to know if it's a theorem, well, I say, is it the first thing in the list? No. Is it the second thing in the list? No. Is it the third thing in the list? And if it is a theorem, I know it will be in the list somewhere, but I don't know where it turns up. And so if I'm not a theorem, I'll just be waiting forever to see, maybe I checked the first million, but I can't stop because maybe this non-theorem is actually the 1,000,001st element of my list. So it's a rather subtle point, and it's not going to matter for us, but it is a good thing to keep in mind. I just morally felt like I needed to give that warning. OK, so a theory is called complete exactly when we can solve this problem. So a theory is called complete whenever either phi or not phi is a theorem. That is, my theory should have an opinion on every sentence. And this does solve the problem because now a non-theorem exactly means that not phi is a theorem. So now I can decide any complete theory. Because if I have a computably enumerable set of axioms, then I can list all of the theorems. But if I'm a non-theorem, then my negation is a theorem. So for any sentence I'm interested in, either phi or not phi will show up on the list. And I know that one of them will be there. So I only look as far as I need to find one of them. And then I know T's opinion on phi. So this is a decision algorithm for complete theories. So what does that mean practically? What are some complete theories that we can study in this way? Well, if you have any question about algebraically closed fields, a fixed characteristic, if you have an opinion about dense linear orders without endpoints. So a dense linear order is a linear order, and it's dense. So between any two elements, there's another element. And it's without endpoints. So that goes without saying. It extends infinitely in both directions. So the canonical model of dense linear order without endpoints is the rational numbers with its usual order. But for instance, the reals is also a DLO, and so on. OK, if you just look at the theory of the reals, if you've done any real algebraic geometry, you've probably heard this. The theory of this is called the theory of real closed fields. That's also decidable because it's complete. If you take your favorite finite structure, then this theory is complete for kind of silly reasons. Because the theory of any structure is complete because any fixed structure has an opinion on everything. And since the group is finite, there's only finitely many axioms because you can literally just write down the multiplication table in finite time. So if you have any question about these and lots of other things, a computer can just tell you the answer. So let's catch some techniques for seeing this. But before we move on, do people have questions about this? I know we went through a lot there, especially the stuff on computable enumerability. So if we want to take a second, pause, catch our breath, that's also fine.
I had a really quick question. Are the 0 ones just true, false?
No, so the 0, 1s are, so algebraically closed fields are the 0 element of the field and the 1 element of the field.
Okay, gotcha.
Yeah, so I'm naming elements of my structure. Yep. And similarly for the reals. Just like when we were talking about finite groups, the 1 element represented the unit of the group. Okay, there's something in chat. How do you prove if a theory is complete? That is the next slide. There's a couple there's a couple ways of proving completeness, and we're gonna go over 2 or 3 ways of doing it. Cool. So let's go on. So let's prove that algebraically closed fields of characteristic P is a complete theory. So the idea is use some heavy machinery from model theory. So maybe here's another reason to learn model theory if you're interested in these kinds of things. So we use what's called the Wash-Vaught test. And yes, that is pronounced wash. And this says, if for some cardinal kappa, if our theory has exactly one model of cardinality kappa, then T must be complete. And this is basically a corollary of the Lowenheim-Skolem theorem, if you remember that from last year's talk or last semester's talk that I gave. But I promise this isn't a hard thing to prove. We just don't have time to prove it in the interest of seeing more decidability results. But this is a fairly low-hanging fruit. But now we use some other heavy machinery from either field theory or algebraic geometry, depending on your bend. So since algebraically closed fields are determined by their characteristic and their transcendence degree, but we're only interested in fields of fixed characteristic, then the field is determined by its transcendence degree. But if I have any uncountable cardinal kappa, then their transcendence degree must be kappa as well. So any 2 uncountable algebraically closed fields are isomorphic of the same characteristic, obviously. But this is exactly the criterion we need to make the Wash-Vaught test go burr. And so we're done, and algebraically closed fields of character P are complete. So I glossed over 2 heavy-hitting theorems here, but you can take my word for it that this proof works, and a model theory class will teach you all about these things. Okay, so let's see another theorem. Let's see that DLO is complete. So again, we could actually argue by the Wash-Tarski. Whoops, that should say Wash-Vaught. My bad. My apologies to Vaught. Anyways, we could argue by the Wash-Vaught test again, since any countable model of DLO is isomorphic to Q. And so there's exactly one model, there's one countable model up to isomorphism. And so Wash-Vaught gives us the claim. But in the interest of showing other ways to get completeness results, let's talk about quantifier elimination. So quantifier elimination does what it says on the tin. It says a theory has quantifier elimination if any sentence in that theory is equivalent to a sentence without quantifiers. This is a very powerful result. And oftentimes in practice, the first step to understanding a theory is to check if it has quantifier elimination. And often, if it has quantifier elimination, it's a very nice theory. And it's not immediate that the theory is decidable once you have quantifier elimination, but many times in practice, that turns out to be the case. So it's a good technique to see. And why, in this case, does quantifier elimination guarantee decidability or completeness? Well, there are no constant symbols in this language, right? The only thing we can talk about is less than. So if I'm quantifier free, I can't actually refer to any points at all. And so the only quantifier free sentences are the empty true sentence and the empty false sentence. And I know that DLO has an opinion on each of those, right? So if I have some sentence and I eliminate all the quantifiers, at the end of the day, I'm going to get true or false, which of course tells me whether or not the original sentence was true or false. And so the theory must be complete and is decidable. Okay, and indeed, I just wrote down what I just said. So how do we actually go about eliminating quantifiers? The answer is combinatorics. So this is a lot. And I'll leave it to you to spend some time on this slide yourself, if you care to. But combinatorics saves the day. So remember, the only symbol we're allowed to use is less than, and you can always use equality. So that means we get less than and less than or equals. And the only thing that these can be glued together by is ands and ors without loss of generality. So by liberally applying De Morgan's laws, you can do some combinatorics to see that you can push all of the negations inside, and you can bring every formula to like a CNF or a DNF. I can't be bothered to figure out exactly which one is relevant here, but you can put it in a special form where you always have a bunch of ors of ANs. But then we can push any existential quantifiers inside the ors, and we can eliminate quantifiers from each of these formulas separately. So that tells us that it suffices to eliminate quantifiers from a sentence of this form, where I have an existential quantifier, and then I'm allowed to say some stuff is less than or equal to my quantified variable, some stuff is strictly less than my quantified variable, some stuff is greater than or equal to my variable, and some stuff is strictly greater than my variable. But a moment's thoughts, or Shala would just say think, shows that we can eliminate quantifiers from a sentence of this form. Indeed, we can just compare everything to X, and by the denseness assumption on dense linear order, if I know that this condition is true, then I'm guaranteed to be able to find an element which is living inside all of them, or living between all of them. So you can check that all I've done here is I've said like, so here, when do I know there's something between all the yi and all the zl's? Well, that happens exactly when each yi is less than each cl. Okay, and then you can also check for the strict inequalities one, this has to be a strict inequality, and so on. Yeah, and this is a quantifier-free sentence, so we can eliminate quantifiers from formulas of this form, but then by liberally applying De Morgan's laws, we show that we can eliminate quantifiers from everything. If you're interested in this, quantifier elimination is a very fun way to sort of get your hands dirty and do like really comprehensible combinatorics to see why a certain theory is complete. Okay, do people have questions about this? Or also, I forgot to ask for questions at the end of ACFP. So if people have questions about this, we can take a second. I know this slide in particular is rather busy, but I promise if you spend some time thinking about it, you'll see why this is true. The relevant thing is denseness. Okay, I guess you also need without endpoints. But yeah. Okay, so it looks like there's no questions. So let's move on. Why is the theory of a finite group complete? Well, I said we were moving from most abstract to least abstract. And you can see by the size of this box that this is an easier proof. And so let's work with Z mod 3 is like my favorite finite group. So we're looking at all of the formulas which Z mod 3 thinks is true. Well, this is obviously complete because Z mod 3 has an opinion on every sentence, because Z mod 3 is a group. And you can ask, hey, does Z mod 3 think this is true? So the theory of any fixed model is automatically complete. And so if we want to if we're only interested in one model, then the obstruction to decidability is, does the theory of this model have recursively enumerable axioms? And the answer for Z mod 3 is yes, because it's a finite model. So we can literally just write down the multiplication table of my group, which I'll leave it to you to check that the multiplication table plus the group axioms axiomatizes this theory. Okay. And again, it's not too surprising that a finite structure should have decidable theory, right? If you give me some sentence and you ask, is this true for Z mod 3? It makes sense that you can just check, right? I mean, there's only, every time you see a universal quantifier, you just check all three elements. And every time you see an existential quantifier, you check all three elements. So I guess that means this theory has quantifier elimination. Yeah, okay, so there's another way to prove that this works. But you can imagine that this is somewhat obvious, but this leads you to a question. Can you run a similar argument for any infinite theories or for any infinite structures, right? So we've shown that the proof that Z mod 3 has decidable theory is, well, check, right? Are there any infinite structures for which the proof is also just check? And the answer is yes, provided all of the functions and relations are simple in a certain sense, by which I mean computable by some finite state machine. And that's going to be the topic of the next section of the talk. So we're now done with completeness. So if you have any questions about completeness, feel free to ask, because we're about to move on to automaticity as a way of proving that a theory is decidable. Give people a second to ask questions.
Can you give an example of what like a sentence would be?
Yeah, so a sentence is any question you can ask of a group that doesn't have free variables. So for instance, you could ask, for all x, for all y, xy equals yx. And that's a sentence. And Z mod 3 thinks that that sentence is true, right? Because that sentence says, I am an abelian group.
Or you can ask, like, does every element cube to the identity or something?
Exactly. Yep.
Okay.
So anything that you can write down, but the only symbols that you're allowed to use are the group product, the inverse, and the unit element. But if you can ask your question using only those symbols and first order logic, then you're a sentence in the theory of groups.
Okay.
Cool. Okay, so let's move on to automaticity. So a structure X with operations Fi and relations Rj. So you can imagine the Fi are like group multiplication or addition in rings. And the relations are things like an ordering or an ordering, like a subset if you want to have a distinguished subset. This is called automatic if my set is isomorphic to a set of words over some alphabets, where each Fi and each Rj can be computed by some finite state automaton. Now, the actual definition of an automaton is not worth showing in this talk. It's technical, it's gross, and all it's meant to do is formalize a very intuitive idea, which we can talk about. If you've ever seen the like 7-tuple definition of a Turing machine, you know how unenlightening these definitions are. So I'm just going to save us all some time and not give it. Instead, I'll give a definition by example. So I'll showcase why the group addition in the integers is automatic. You can imagine. Automaticity basically says there is some simple algorithm that you can do to compute all of the operations. And thankfully, for the integers, we have a very simple algorithm for computing addition. It's the one that you learn in like 2nd grade or whenever you learn addition, right? You line everything up, and occasionally you have to carry numbers. Cool. So we'll talk more about that. So exactly. So the structure to keep in mind is the integers with addition, and you can actually get less than or equal to out of this as well. But you can't get multiplication. Okay. So step 1, we have to identify Z with the words over some alphabet. We could use all of the words over this alphabet. Okay, you want a subset of the words that's recognizable. So it's obvious that you can write something that will recognize it starts with a minus sign or there's no minus signs. But we'll go ahead and use the negative sign and we'll write it in binary instead. And we're going to represent our numbers by their binary extension, possibly with a negative sign at the front. There's only one minor technicality, and that's we usually ask for our automata to read strings left to right, because at least in the English-speaking world, that is the natural way to read a thing. Except we have this asinine historical carryover where we add our numbers from right to left, right? And so you can imagine, yeah, this is a tricky thing that you have to get over. And so since I never gave you the definition of an automaton, I could just say, oh, automata read from right to left, and you would believe me. But rather than modify the definition of automaton that I didn't give, we're going to retroactively fix this historical mistake, and we're going to write our integers from left to right in order of increasing significance. Okay. So for instance, 8 will be represented 0, 0, 0, 1, because here's the 1's place, the 2's place, the 4's place, and the 8's place. And -6 is negative. We have a 2 and a 4. Why we don't always write our numbers like this is silly. This is a problem. If I could go back in time and change mathematics, I would solve this. But alas, much like writing function application on the left, this is what we're stuck with. Okay. So in the interest of simplicity, I'm only going to give a machine that works for positive numbers. I'm simplifying dramatically here so that we don't spend all day on this one example. But you can imagine, and it's maybe a fun exercise, to extend this machine to work for negative numbers as well. Moreover, in the real world, logicians actually use what's called a Bucci automata. And I'm going to be presenting what's called a Mealy automaton. This is an entirely technical distinction. You do not need to worry about it. But I know that if my advisor from undergrad ever saw these slides and he saw that I put a Mealy automaton here, he would yell at me. And so this is entirely if someone else ever reads these slides. Again, I'm presenting Mealy automata because they're easier to understand. Bushi automata work on infinite words, and they have a rather technical condition for how you go about accepting strings. So we're not going to touch that, but know that in the real world, people actually use a different kind of automaton. Okay, but this still showcases the idea of an automatic structure, and it's going to be good enough for getting an intuitive grasp of what's happening. So bam, here's the automaton. We have two states. We have a state called no carry, and we have a state called carry. We're going to start in the no carry state, and we're going to read our input bits one column at a time. So if I see a 0 and a 1, and I'm not carrying, I spit out a 1, and I'm still not carrying. If I'm not carrying and I see two 1s, then I should spit out a 0 and carry a 1. And I claim this automaton actually performs addition for us. So let's see why. Let's go through an example. Let's go ahead and add, I believe this is 11 plus 9. You can check me. So let's do it. So we start out in the no carry state. We look at the first column. We see two 1s. So that tells us output a 0 and move to the carry state. Now we're in the carry state. We see a 1 and a 0. So that tells us to spit out a 0 because 1 plus 0 plus the 1 that we're carrying is a 0. And we stay carrying. So we output a 0 and we stay in the carry state. Now we see two 0s. So that tells us to output a 1 and move back to the no carry state, which is exactly what we do. We see two 1s. That tells us to move back to the carry state, output a 0. And now, minor technical gripe, we ended in the carry state. So that tells us to put one extra 1 at the end. Okay. And you can see, remembering that we're reading our digits left to right, we've successfully added 1 plus 2 plus 8 is 11, plus 1 plus 8 is 9, 9 plus 11 is 4 plus 16 is 20. Hey! And we succeeded. Okay, any questions about this? I claim automata theory, actually constructing automata, is basically doing this, but for more complicated structures. And you can imagine this is a combinatorial problem, which again gives us a nice way of talking about structures that might otherwise be quite complicated. Do people have questions about what happened here? Again, glossing over the Bushi-Mealy deal.
So then would we use this to like create in a computer program, or what is?
Yeah, exactly. So the idea is that sort of everything we might care to know about an automaton is baked, or everything we might care to know about the structure is baked into this finite state machine. And so I didn't put slides for this in the talk, but I didn't actually describe how you solve the problem with this. So I'm glad you asked. I think my next slide is literally just, yeah, okay. So a brief guide for how to decide the theory of an automatic structure. So what you do is, if you have some question, here's what you do. It turns out that logical operations correspond to operations on machines. In fact, if you care, this can all be made functorial from the category of machines to the category of like logical sentences. Anyways, I'm getting beside myself. So for instance, if I want to look at, so formulas are built up recursively. So at the bottom level, I have my primitive relations, and then inductively or recursively, if I have two things that I've already defined, I can glue them together with an and, or I can glue them together with an or. And if I have a sentence with some free variables, I can stick a quantifier in front. So there's this inductive definition of formulas. And since I know by the assumption on automaticity that there is some finite state machine that talks about each of the primitive operations, then if I can figure out how to do all of the inductive operations by gluing machines together, then that gives me, at the end of the day, some finite state machine which represents the sentence that I'm interested in asking about. And it turns out, so you can see the addition thing, right, has two inputs and one output. So it has, you can imagine it taking in 3 tapes. So you can imagine here's 3 tapes that we're reading. And every time I use a quantifier, I kill a tape. And so at the end of the day, if I have a sentence, there's actually no tapes at all. And what that means is I have just a labeled graph with finitely many vertices, a distinguished start node, and some distinguished nodes which corresponds to, yes, this is true. And it turns out that the theory is decidable exactly when there is a path in my graph from the start node to one of the accepting nodes. And if it's a Bushi automata, you also need to know that there's a cycle, but again, we're not, that's a technicality. And so what this tells us is that we can glue all of my finite automata together. And at the end of the day, we're left with some new finite automaton. And the sentence is true exactly if there's a path from node 1 to one of the accepting nodes. And checking if there's a path in a finite graph is definitely something we can do. And so it turns out the theory of automatic structures, you can actually get really tight bounds on how long it takes to decide a certain problem. Does that make some amount of sense? I should have probably included a slide on it.
Yeah.
Sorry, I coughed.
Sounds good.
Okay, perfect. So again, I mentioned none of that because it's rather technical. But why do we care? There's something in chat. That makes sense. Awesome. So why do we care? If A is an automatic structure, then the theory of A is decidable, which for exactly the reason I just outlined. And in fact, you can add bonus quantifiers to your logic, and the theory remains decidable. So if you have questions that ask, are there infinitely many x, and are there n mod m many x, you can actually still decide these questions. So for instance, in the theory of the integers, you can ask, are there n mod m many things which are, and then you write some sentence in the theory of the integers with plus and less than or equal to, which is very cool. Yeah, so we can actually make our logic slightly stronger and still retain decidability. So what are some automatic theories? When can we apply this machinery? Well, Pressburg arithmetic is decidable, or is automatic. So we just proved this, right? Well, I showed you addition, but you can imagine checking if a string represents 0 is very easy to do. And checking less than or equal to is also very easy. You just see which one has a 1 first, right? Another reason to read left to right. Okay. For Skolem arithmetic, which is instead of working with plus and 0, you work with times and 1. It turns out this is also decidable. And you can imagine you're going to need a different way of coding up your numbers. So just binary won't work. As a fun exercise, maybe try to come up with an encoding in which a finite state machine can do multiplication. I will tell you, you're going to want to think about primes. Okay, so that's a fun exercise. And then this is a different result. So you really need the full power of Bushi automata to get this. But this is a very famous result, and I had to mention it. The monadic second order theory of the natural numbers with the less than relation is decidable. And that is basically an automaticity results. This is actually the reason that Bushi invented his automata back in like the 70s or whatever. So this says any question you have about the natural numbers, where not only am I allowed to quantify over the naturals, I'm actually allowed to quantify over subsets of naturals, which is really shocking because there's like non-computable subsets of naturals. You can actually answer any question about this. Okay. And a brief like caveat lector, in geometric group theory, there's another notion of automatic group, which is defined by Thurston to do geometric group theory. And it turns out that Thurston automatic groups, and if you need to disambiguate, you would call one of these a word automatic group. It turns out that word automatic groups and Thurston automatic groups, they have overlap. For instance, the integers is both Thurston and word automatic. But there are counterexamples in both directions. So there's things which are Thurston automatic, but not word automatic. And there's also word automatic things that are not Thurston automatic. So if you're familiar with Thurston automaticity, be a little bit careful because this has tripped me up on a couple occasions. Okay. So do people have questions about any of this? I'll give people a second. Okay. So this is great and all. But are we in risk of being put out of a job, right? I've just said that all of these lovely things, even such surprising things as MSO less than, are decidable. So a computer can just answer any question you want about them. Are the computer overlords coming to ruin our life and take our jobs? theorem, no. So let's see some theories which are not decidable. And again, if you're, depending on your definition of optimism and pessimism, this is now the half for the other people. You know, if you're an optimist and you think optimism means computers can do lots of stuff, then this is now the part of the talk for the pessimists. Or if you think that optimism means that computers can't take our jobs, then the last bit of the talk was for the pessimists, and this is for the optimists. Okay, so let's find some theories for which no algorithm can possibly answer, is phi a theorem? So first of all, ZFC or ZF, any set theory worth its salt is undecidable. You can imagine, right, that this makes perfect sense. But indeed, the theory of the natural numbers with plus, times, 0, and 1, indeed, the theory of piano arithmetic is beyond computers as well. So this is called the theory of true arithmetic, which is, you can imagine, there are these things called non-standard models of the natural numbers, which have all the same first order properties of natural numbers, but have other weird things. So like an infinite natural number might exist. And it's not possible just by probing with first order theory to tell the two apart. And so this leads to some philosophical issues because I can't tell if you and I are talking about the same natural numbers. We as humans have some idea of what the true natural numbers are, but it's not actually possible to write down what we mean by the true natural numbers, at least in a first order way, which is really, really cool and really confusing. And there's lots of really deep mathematics there. But it turns out for that reason, for the existence of these non-standard models, means that the theory of true arithmetic, or the theory of what we mean when we say the real copy of the natural numbers, is not a computable thing to check. Rather interestingly, the theory of groups is undecidable, but the theory of abelian groups, is decidable. So the fact that the theory of abelian groups is decidable is a theorem due to Wanda, some Polish last name, who was a badass mathematician, and she's awesome. And the fact that the theory of groups is undecidable basically comes down to work of Novikov-Boone, if you're familiar with that theorem. But yeah, it's really, really interesting that if you have a question and you want to know, is this true of all abelian groups, that's answerable. Whereas, is this true of all groups? That's unanswerable, which is kind of interesting. And all of these undecidability results basically rely on the halting problem, which if you're familiar with it, you know what it means. If not, then the halting problem is sort of everyone's first example of an undecidable problem. So the halting problem is if I give you some program and some input, and I ask you, does this program halt when I run it on this input? That is in general, it's an unanswerable question. And so the best you can do is run it and wait. And so because the halting problem is undecidable, you can code up the halting problem in a lot of these ways, and that shows you that arithmetic is undecidable. So we're going to see an example of that on the next slide. So theorem, the theory of the natural numbers with plus, times, 0, and 1 is not decidable. Proof. So step 1, let M be your favorite Turing machine, or register machine, or Magic the Gathering, pick your favorite Turing complete model. Step 2, be clever. This is the most difficult step of the proof. Step 3, in step 2, you would have shown that there is a formula phi sub m corresponding to this Turing machine, such that phi sub m of n is true if and only if m halts in less than or equal to n steps. So it turns out you can, this is called arithmetization. This is a trick invented by Gödel and others. And you can actually code up the notion of a Turing machine running as some sequence of numbers. And it turns out that everything in sight is computable, and everything in sight is representable by some first order formula with plus and times. And so what this means is that you can come up with some first order formula where phi m of n is true if and only if my Turing machine halts in at most n steps. But now we have an issue, right? Because then if you could tell me whether there exists an n such that phi m of n, then you would solve the halting problem, because this sentence exactly says that m halts. And so there can be no algorithm to decide whether this sentence is true or false. So there's certainly no algorithm to decide the whole theory of n, because this is, among other things, in the theory of n. So that was deep and a lot, and I glossed over a lot of stuff. But do people have questions about at least the outline of this proof? This be clever step is doing a lot of work, you can imagine. This is due to very deep work of like Kleene and Gödel and others. Okay, cool. So let's move on. But now that we have this and we've sort of put all of our cleverness into showing the natural numbers are undecidable, or the theory of the natural numbers is undecidable, we can show other theories are undecidable by showing they can simulate the natural numbers. Yeah, I wish I could use be clever as well. I almost included that, you know, the cartoon from like 100 years ago of like, do this, and then step 2 is that a miracle occurs, and step 3, it's like a guy on a blackboard. It's a very funny cartoon. I almost included it, and then I didn't. Okay, so let's try to simulate the natural numbers. So for instance, the theory of the integers with plus and times isn't decidable. Why? Well, a theorem of Lagrange, so a very classical theorem in number theory, shows that every non-negative integer can be written as a sum of 4 squares. Let's check chat. Instead of QED, same. Okay, so, but what does this mean? This means we can code up the natural numbers as all of those integers, which are the sum of 4 squares, because the sum of 4 squares must be non-negative. So we can code up the natural numbers in this way. Then if we could answer every question about z, we could answer every question about n by asking it for z, but requiring that our answers satisfy this bonus principle, which is obviously a thing that we can write down using plus and times. I mean, I basically did, right? So since n is undecidable, or that should say the theory of n, sorry, since the theory of n is undecidable, the theory of z must be as well, because we could use the theory of z to decide the theory of n. So how do people feel about this? Lots of undecidability proofs basically come down to this. If you're familiar with like proofs of NP completeness and stuff, it's very, very similar argument structurally. I'll give people a second to ask questions. There's some stuff in chat. The rest, same. Okay. So as an interesting aside, so this is not immediately related to decidability, but we're close enough to it, and it's such a cool result that I have to talk about it. Not only is the theory of the integers undecidable, but the simpler question, does the polynomial p have an integer root, is already undecidable. If you have like more than 9 variables is enough. Obviously with one variable, you can decide it by like, I don't know, take a number theory course or something. But okay, so indeed, Hilbert's 10th problem asked if some algorithm could tell if a Diophantine equation was solvable. That was Hilbert's 10th problem, and we know the answer is no. This is a famous theorem due to Metiasevich, as well as Putnam Davis and Julia Robinson. Wait, yes, Julia Robinson is the mathematician, Julia Child is the chef. Okay, so in fact, this was shown by showing something really, really cool. If you'll indulge me, like I said, I need to talk about this theorem because it's so cool. So this is the Metiasevich, Robinson, Davidson, Putnam theorem, which is a mouthful, so people call it the MRDP theorem. Every computably enumerable set, so the same thing we talked about from before, where if there's a computer program that lists this set, then the solution set is actually the solution set to a Diophantine equation, which is so surprising. So for instance, the halting problem, sufficiently coded, is a computably enumerable set, right? Because you can imagine, I said earlier that you can build this sentence phi sub m, then projecting down, you can just check, is phi sub n of 1 true? Is phi sub n of 2 true? Is phi sub n of 3 true? And you can keep doing this, and eventually you can check the halting problem in a computably enumerable way. But because of this, that means that you can code up all of your halting Turing machines as the solutions to a Diophantine equation. And so if you could solve all Diophantine equations with parameters, you could solve the halting problem. So Hilbert's 10th problem is unsolvable. But what does this mean, right? It's not clear how you would go about coding up some set as a Diophantine equation. So let's see some examples. So first, let's start with the Pell equation. If you've ever seen a class in number theory, you'll be familiar with this equation. So it says that x squared minus ny squared equals 1. It turns out that this Diophantine equation, this is a Diophantine equation with parameter n. And it turns out that this equation has solutions if and only if n is not a perfect square. So there's always the silly solution, and we add 1 to y to get rid of this silly solution. And so what this does is this Diophantine equation is solvable if and only if n is not a perfect square. So that means, this formula here, there exists an x and a y such that the Diophantine equation is solvable, defines the computably enumerable set, the set of all n for which n is not a perfect square. And it turns out you can do this with any computably enumerable set. And I believe it's constructive. I think you can actually like turn the crank and find such a Diophantine equation. Similarly, this equation here determines the set A for which A is not a prime. Or I guess you want A is greater than 2 and A is not a prime or something, right? Because I can factor A if and only if A is not a prime. So with A as a parameter, this Diophantine equation has a solution exactly when A can be factorized, exactly when A is not a prime. Okay, so Matiasevich promises that we can find such an equation for any computably enumerable set. And as I said earlier, it turns out that you can always do it with you never need more than 9 variables. There we go. So an obvious question, the primes are a computably enumerable set. We saw on the last slide that checking not primeness is quite easy. Can you check primeness? Is there a polynomial so we know there is one abstractly, but has anyone found a polynomial whose Diophantine equation is solvable exactly when you set the parameter to be a prime? Yes, theorem, this polynomial works. You'll forgive me for not retyping this polynomial. It's a polynomial in 26 variables plus k. And according to Wikipedia, you can bring the number of variables down to 9 as promised, provided you make the polynomial have degree about 10 to the 45, which makes sense. You need to put the complexity somewhere. And conversely, you can get the degree down to 4 if you're willing to use 58 variables. But this is extremely cool, right? So if you plug in k plus 2 as a prime number, it turns out that this polynomial is satisfiable exactly when you instantiate k to a prime number. How cool is that, right? Like, why should this exist? Anyways, I love this result. I love this result. So this poses a really interesting question, right? We know that the theory of the real closed field is decidable. So there's an algorithm which decides if a polynomial equation with parameters is solvable over the reals. And this makes sense, right? Even like in the most silly way, you can check if a polynomial is solvable over the reals by the following algorithm. Graph it and look at the x-axis, right? The real numbers were created to make solving equations easy. So this should make sense that this should be decidable. But we've just seen stuff in chat. Is there a name for those polynomials for the primes? Yeah, if you look up like prime generating function, these are also sometimes called Matiasevich polynomials, or Diophantine sets would be another thing to Google. These are all keywords. But yeah, if you Google prime generating function, if you go to the Wikipedia article for that, there's a description there, and you can probably find references there. Okay, so we've just seen that there's no algorithm to solve polynomials over the integers. Question, what about Q, right? That's an obvious intermediary ring to consider. And now it's time for the interactive portion of the talk. Go ahead and say in chat, or give me like a thumbs up, thumbs down, or whatever, if you think that there's an algorithm that can find the rational roots of a polynomial with rational coefficients. I'll give people a second to say things. If you're using your thumbs up, thumbs down, I'm not sure if I can see it. How do I, let's check like participation. Is that what I do?
Yeah, I think it's under participants.
Participants. Okay, so we have 1 yes, 1 no. We have some yeses in chat. We have 1 no in chat. Okay, interesting. Really, really interesting. Okay, this is super open. Like, we know next to nothing about this problem. So genuinely, any of you can be right. It's a really, really exciting question right now with tools from number theory, algebraic geometry, model theory, computability theory. It's a really, really active branch of research in logic right now. So if you're interested in these problems, definitely give it a look. The other really famous open problem in decidability is if you look at, so we know about the real numbers with plus, times, 0, and 1. What if we add exponentiation to this? So we now allow ourselves to take e to the x as well. Is that theory decidable? And it turns out that's also super open. That's a problem due to Tarski from like 100 years ago. And that's open. And it turns out that that question is reliant on a question from either complex geometry or number theory, depending on who you ask, called Samuelson's conjecture. I think Samuelson's conjecture, some S word. Anyways, if you Google like theory of the real exponential fields, you'll find it. Anyways, super cool. Lots of really, really interesting open questions in decidability. And so one last parting note, let's define the kissing number in Rn. This is the largest number of non-overlapping unit spheres which mutually kiss one central sphere. So for instance, when n equals 1, the kissing number is 2, because there's no way you can put more than 2 unit spheres kissing the central sphere. When n equals 2, the kissing number is 6. You can pack 6 spheres, all of which kiss a central sphere. Question, what is the kissing number for n greater than or equal to 5? This is totally open. I think there's some bounds known, but broadly, the exact number is open. And it turns out that this problem can be expressed as a first order formula over the real field with the real order field. So as we now know, the theory of that structure is decidable. So you can just ask a computer what the kissing number is for n greater than or equal to 5. It'll take a while to run, but you can do it. Why think? Just ask a computer. Anyways, thank you. That's we're only a few clock cycles away from solving that problem, but that's all I have. If people have questions about things, I think I went like a minute or two over. Sorry about that. I was supposed to finish at 1:50, but I think I got a little bit too excited with Matiasevich's theorem. Okay, so I'm going to go ahead and stop the recording. And then if people have questions about things, we can hang out for a little while and talk. Okay.
Awesome.
So yeah, do people have questions about things? Where are folks answering these questions? I'm probably gonna, oh, what do you mean, like what papers and stuff people are using to answer these questions? Did I not stop the recording?